Hi there. So what we're going to do today is we are going to do some internal analysis of a piece of brass. We are going to take brass, and if you look at brass, it is an alloy of copper and zinc. Remember, there are two main kinds of alloys: substitutional alloys, where the two metals are actually relatively close to each other and they just take each other's positions there, and then interstitial alloys, where there is a big difference between the sizes of the atoms and the smaller atom fits in between the atoms of the other one that is there. Taking a look at copper and zinc on the periodic table, we can see that they are literally right next to each other. So that really would imply, especially being in the same row as each other, that they're at the same energy level, roughly the same size, and so forth. So you are going to be looking here at a substitutional alloy between the copper and the zinc that is there. So again, the whole idea of an alloy is you take a pure metal and you either substitute out some of those atoms or fit in other atoms in between those guys. What we are going to be doing is we are going to be reacting away the copper aspect of things. We're actually also going to be reacting away the zinc, but we're not going to care about the zinc as much. Why aren't we going to care about the zinc? Because take a look at these charts here. We can see that this guy here is copper, and here's another one that's copper, and we can tell that with our copper absorbances, we get some up and down action going on here for it, which is why copper is our traditional blue color that we are used to seeing. Now take a look at zinc. Zinc down here has a flat line, all right? So consequently, this is telling you that this is a colorless solution. So because zinc is colorless, we can react both of them away and keep them together, and using a colorimetric analysis, the zinc is not going to interfere with our investigation into the copper that is there. So what we are going to do is we are going to take our brass screw and we are going to react it in nitric acid, and in doing so we're going to get the following net ionic equation out of this. So if you take a look at this guy, remember the whole idea of a net ionic equation is that anything that is aqueous and ionic splits up into its pieces, and when it splits up into its pieces, if you have anything that's the same on both sides, you can cancel them out. It also works with solids and liquids. Water is often something that is canceled out, but this guy here is aqueous and ionic, so he's going to change into 4 hydrogen ions and 4 nitrate ions, like so. All right. And the only other thing that's going to break apart over here on this side is this guy, who's going to break into the copper ions and then 2 nitrate ions. So in order to turn this into a net ionic equation, all we have to do is take the 2 nitrates that are over here and cancel out 2 of them that are over here, and then we're left with 2 instead, and then we have everything else that we need. So that is your net ionic equation. So again, the idea of a net ionic equation is that you split up ionic compounds, and then anything that appears the same on both sides is canceled. I should say you should split up aqueous ionic compounds. If it's a solid, then you keep it together. All right? So now what we're going to do is we are going to take a brass screw, and we are going to put it on a scale, and we're going to measure its mass to figure out how much it is in totality, and then we're going to react it away. So I've already done that. I have put a brass screw on the scale. I don't know if you can see it, but there he is. I've taken a piece of brass and put it on a scale, and I've got a total mass of about 1.0165 grams. So the total mass of my brass screw is just over a gram that is there. And now what I'm going to do is I'm going to take that screw and I'm going to put him into nitric acid as indicated by our equation up here, and we are going to reactify him away. Pay particular attention to the brown gas that is formed. That is the poisonous nitrogen dioxide gas that we will see. Alrighty, so what we're going to do is we're now going to try to dissolve this brass screw, and we're going to dissolve it in some nitric acid. So first things first, Going to go ahead and put the brass screw in there. Next things next, we're going to take the nitric acid, and after our calculations, we're going to need about 5 milliliters of it. So I'm going to go ahead and add in my 5 milliliters here. So in it goes. There's my 5 milliliters. I don't have to be exact on this, but I just wanted to be in the neighborhood. And then I'm going to go ahead and pour this in here. And immediately this is going to start to react, and it's going to put the nitrogen oxide there into the air. You can see that that brown yucky gas is already beginning to form, and that is not good for anything. So we're going to have to take this whole thing and we're going to put it in the fume hood over here and let that dissolve and react overnight. So that guy there is going to sit all night and react. Can you tell that the blue color of the copper ions is already forming down here? So this guy there is going to work all night, and we're going to get rid of that poisonous gas. So here is our volumetric flask after having spent all night reacting and having time to get all the brown gas out of there. Although, to be honest, from where I'm standing, there's still a tiny little bit of brown gas in there. And you can tell that the copper ions are there because we've got the blue color that is there. And so now what we're going to do is we are going to take this guy and we're just going to add in water until we get up to our line, because remember, the whole point of a volumetric flask is that there is only one line that's there. And when I do that, I then know that I have a 1 liter of this particular solution that is here. And I'll do that now. So I have added in a bunch of water to our solution and diluted the heck out of it. I'm not quite done though. So remember that what you want to do is you want to kind of get this guy close, but then you want to get right to that line so the bottom of the meniscus hits exactly on that line. So what you really want to try to do here is you want to add in, and at this point I usually use a dropper. It's tough to do this and film at the same time, so you might see a slightly different perspective than what I see. But we make do with what we have, right? Alright, so we go ahead and add that in so that the bottom of the meniscus is right there. And if you are looking right at it there, it should be right at that line there. So the meniscus is right on that line. So now I have exactly 1 liter of this solution that's there. Alrighty, so what we're going to have to do here is we are going to have to set up a set of known chemicals, known concentrations, excuse me, for the Beer's Law. And so we are starting here with a 0.4 molar solution that I made myself, so I know that one is fine. And what we're going to do is we're going to try to make a serial dilution of 0.2, 0.1, 0.05, and 0.025 for these. And it's going to be very simple the way that we go about doing that. So here's what we are going to do. What we're going to do is we are going to take our volumetric pipettes, and I've got a tenor here, right? And I'm going to put this guy in, and I'm going to use the volumetric pipette to get 10 milliliters exactly of this solution here, like so. So there's 10 milliliters there, and then I'm going to add that guy in there like so. And then, because I know that that is 0.4 molar, and it's 10 milliliters of it, if I want to turn that into 0.2 molarity, right, that is going to be cutting my molarity in half. Well, if I'm going to be cutting my molarity in half, then all I really need to do is add an equal amount of water. So if I take one of these guys here and I add 10 milliliters of water to this, like so, and get exactly 10 milliliters of water here. Now I have doubled the volume of that from 10 to 20. And so in doubling the volume of that from 10 to 20, I'm going to be cutting my concentration in half for this guy. So that guy there is now 0.2 molarity because it is that concentration cut in half. So all I'm going to do now is take this and shake, 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 make sure this guy is good and mixed. And if I make sure that this guy here is good and mixed, now I've got myself a 0.2 molarity solution. So you can actually tell right off the bat, that's a little bit easier in person than perhaps it is on camera. But the one on the right is lighter than the one on the left because, again, we have cut the concentration of it in half. So now what I'm going to do is I'm going to do the next part of my serial dilution, which is to take this guy and take 10 milliliters of this, which is now 0.2 molarity, right? So that's 0.2 molarity, and put it into the next one. And by taking 10 milliliters of the 0.2 molarity and putting it into the next one, okay, and now I have that. And now what I'm going to do is I'm going to take this guy here and get 10 milliliters of water. And if I put 10 milliliters of water into this solution, like so, this guy now is going to be a 0.1 molar solution because I have cut it in half again. So I started at 0.4, and I took 10 and added 10 of water, and that cut it to 0.2. And then I took 10 of the 0.2 and added 10 of the water, and that took the 0.2, shakeify that up, and that cut it to 0.1. So now I have cut that in half again. Again, if we take a look at this, you can definitely tell that these are getting lighter and lighter as we go along with them. So now the next step is to take 10 of the 0.1. And if you take 10 of the 0.1 and put it in this guy here, now I've got 10 of the 0.1 molar solution. But again, I'm going to make it easy on myself and cut that guy in half by taking 10 of water. And there's 10 of water. And now, after I do that, it has been cut in half again. So it is now 0.05 molarity for my solution. And that is there. And again, all I got to do is put the cap on and shake, shake, shake this guy up. That's 0.05. So again, by cutting each of these guys in half, I started at 0.4, then to 0.2, then to 0.1, then to 0.05. One more to go. Take 10 of the 0.05, put it in here, my last one, and then add 10 more of water, and shake that guy up. That is 10 of water. And now I have 5 different solutions, all of which I know the exact concentration for because I set them up myself. Put the cap on this, give that guy a shake, like so. And back in the day, before computers, they would just kind of eyeball it. They would take an unknown solution and they would eyeball it and say, well, is it between this and this, or is it between this and this? But we don't have to eyeball it. We have computers, and we have a colorimeter device there. And because we have computers and a colorimeter device, and we know about Beer's Law, we can set up a known plot of all of these 5 and then compare that known plot to, or unknown and see where our unknown fits in amongst all of these. So now what we're going to do is do a Beer's Law analysis of our solution. Remember that our colorimeters have only 3 options for our collection of data. We have a blue light at about 470 or so. That doesn't look very good. We've got a green light at about 565. Maybe okay. Or we've got a red light at about 635. Yep, that's the one that we're going to need. So again, we're going to use our red setting at 635 nanometers in order to collect this data. Alrighty, so what we're going to do now is we are going to set up our Beer's Law examination. So we go here to the desktop and we do Logger Pro. And when we do Logger Pro, we do a file and an open up here at the top. So here's file and open, and we go to chemistry with Vernier. That is right there, chemistry with Vernier. And then we're going to open up number 11, which says Beer's Law. And then it says, hey, do I have an interface connected? I do. I have my USB cord coming over here to my green Vernier Pro box, and then that is set up with a cord here to my Vernier box that is there. So yes, I want to connect with that like so. Connect, please. There we go. And now I need to tear this, calibrate it. That's the right word. I want to calibrate it. So you go to experiment and then calibrate, and then come over here to the Lab Pro 1, and then you're going to calibrate now. And I have got myself a cuvette, and in that cuvette I have just put deionized water. Remember, there's frosted sides and clear sides. The frosted sides go up and down in the colorimeter box. The clear sides go left and right. That line shows you the path of the laser. And we close that up like so. And we need a 0% T here. So we're going to come over here and we're going to put 0% T like so. And you should see a change in your voltage there. So your voltage should go to a certain amount. Fine, give it a minute to think about what it's done. I'm going to now type 0 and go ahead and click keep. All right, like so. And now we're going to use the red light because we've decided that the red light was the correct one. So I'm going to take this and I'm going to turn it over here to the red setting. You should see a major change in the voltage here. If not, then you've probably got a bad box and you need to swap something out here. So please note that we were at 0.75 volts here. And as soon as I change this to red, I should see that 0.75 change to a different number. There we go, yeah. And as long as that number changes, then that probably means that you've got a good box. All right, so we give that a minute to think about what it's done, and that's 100%. So we're going to put 100% there, and then we're going to go ahead and click keep, and then we're going to click done, and our absorbance should read 0 or pretty close to it. Yep, there it is. We are in good shape. Okay, wonderful. So now what we're going to do is we're going to come over here and we are going to take each of our different concentrations. Remember, they are 0.4, 0.2, 0.1, 0.05, and 0.05 and 0.025 that's there. And we are now going to check each one of these in the cuvette that is here. So what we're going to do is we're going to come over here and we're going to click start, or collect, I guess I should say. We're going to click collect, which starts the experiment. All right, don't click stop until you're done. Sorry, excuse me. All right, so now you take the cuvette out of the guy here. I have opened him up and taken that cuvette out that just had the water in there. And now I'm going to take that and I'm going to dump it out. And I'm going to take the 0.04 and I'm going to pour the 0.04 in. So there's the 0.4. Put that guy in. Rinse him a couple times. So there's the 0.4. Put it in, dump it, put it in, dump it, and then fill it again. Should be more than enough. So that's now the 0.4. I come back back over here to my box and I put him in. Again, frosted sides up and down, clear sides left and right. Close him up. And then I come over here and I click keep. Like so. There is keep. And a window pops up and says, hey, what was that concentration? Because it doesn't know. But I do. I know that that was a concentration of 0.4. So that was 0.4 molarities. So I'm just going to go ahead and put in 0.4. And then I'm going to click OK. For there. Oops, see. Yep, great. Wonderful. There's that. And then I'm going to repeat. So I come back over here. Get this guy out of here. Set him there. A couple of hands. Take this guy, dump him down the drain. Now I'm going to get my 0.2. Put in the 0.2. Dump it. Put in the 0.2. Dump it. Put in the 0.2. Like so. Make sure that the outside of this is good and dry. I think I may have spilled a little on there. No big deal. I should be using a Kim wipe instead of a paper towel, but I'm not. All right. Take that over here. Close the lid. Come over here. Click keep. Like so. And now I'm going to type in 0.2. 0.2 that's there. And then I click OK. And I repeat for the others. So take this out of here. Dump it. Take my 0.1. Fill it. Dump it. Fill it. Dump it. Fill it. Like so. Take this guy back over here. Close him up. Here I am. Rock me like a hurricane. I click keep. That's going to be 0.1. Like so. And you'll notice that I'm getting a nice straight line here. See my nice straight line? I should if I have made these solutions properly. All right. Take this guy out. Here's my 0.05. Put in my 0.05. Dump it. Put in my 0.05. Dump it. Put in my 0.05. Like so. So now I got 0.05 in there. Back over to the colorimeter box. Close it up. Come over here. Click keep. Now that's going to be 0.05 that's there. Hit OK. Looking good. One more to go. Stay on target. Dump that. Here's my 0.025. So there's my 0.025. Here's some 0.025. And one more time like so. So that's the 0.025, should be my last one. Put her in. And click keep. 0.025 and hit OK. And look at that nice straight line. Nice job, Mr. Smith. Nice straight line going all the way down to 0, 0. It's there. All right, now that I am done with my collecting, I can go ahead and click stop. And then I can do a linear fit, which is that guy there, linear fit. And I want to make sure I take a picture of that because that is all the information that I need, like we talked about before. I've got my slope, I've got my y-intercept, I've got my correlation, I got everything nice and neat and perfect there. Everything is just about perfect. There's only one last thing that I have to do, and the one last thing I have to do is my unknown. So I don't have to click anything. All I have to do is take my unknown that I made, right? Take the last one that I did and dump it out so that it's empty. take my unknown that's there, get some of it here, and fill it with my unknown, and dump it. And then fill it with my unknown that's there. Again, I'm just taking from my solution that I made from the brass screw that was there. And dump it. And then take my unknown that's here, fill it up, fill her up. So there we go. So this is now completely filled with my unknown that I made. I come back over here, put it in the box, close it up, and I don't even have to click anything. All I have to do now is write down that number. So that number is 0.011 or 0.012 for my absorbance, somewhere in between there. Maybe you call it 0.0115, right? If you want to call it that way. Or you can pick either one of those, 0.11, 0.12, somewhere in that zone. Looks like it's holding off on 2. Now it's going up to 3. We'll call it 2. So we're going to call that 1.012 for the absorbance. That's there. So we now have everything that we need in order to calculate the concentration of the solution, and therefore we can work our way backwards and figure out how much copper was in that thing to begin with. So we have our graph here, and our graph is showing the absorption here versus the concentration, the molarity going on there. And we now know that this is a straight line, y equals mx plus b. So if we do y equals mx plus b, but include the proper arrangements for it, our y-axis is our absorption, and our x-axis here is the concentration. So that's the molarity, right? And then I have given you b and m here and here because we figured those from our experiment. So in reality, our slope is 1.99. So our slope is 1.99, and our y-intercept is this guy here, 00414. So fine, this is 0.00414. And now, if I know this, then I can calculate this, or vice versa. If I know this, I can calculate this. So what is it that I knew about my sample? Remember, I took my unknown sample, and I put it in the machine, and it told me that the absorbance of my unknown that was there was 0.012 absorption units. This was for my big volumetric flask, if you remember, that had the dissolved screw in it, and then I added in all of that water up to that particular line. So a sample of that guy there gave an absorbance of 0.012 units. So if that's the case, then my absorbance is 0.012, that equals all of that. Then I can figure out what the concentration is. 0.012, subtract out the 00414, and divide by the 199 plus tax. It looks like my concentration, it looks like the concentration of my solution here, the molarity was 0.00395 molarity, which again is moles per liter. Now, if that's my molarity, then I can figure out the grams, because don't forget, this guy here was a 1.0 liter volumetric flask. That big volumetric flask was exactly 1 liter. So I know that I have 0.00395 moles of copper per liter. Multiply that by my 1 liter. That gets me moles. And then I know that copper weighs 63.5 grams per mole from the periodic table. So I end up with 0.251 grams of my copper that's there. So if that's the case, and I want to know what the mass percent of the copper is in the brass screw, then all I have to do is take the grams part divided by the grams total times 100%. The grams part is the copper that I'm interested in. That's what I just calculated here. That's my 0.251. My grams total is the total mass of the screw that I started with. And that goes way back to what I started with way back up here. Remember that the screw itself had a mass of 1.0165 grams. So the total mass of the screw was 1.0165 grams. The part on the top was 0.251 grams. So 0.251 grams. So 0.251 divided by my 1.0165 and then reduced to 3 significant figures gets me in the neighborhood of about 24.7% by mass copper. So according to our information, we've got just under 25% copper in that brass screw.